Let's do some Atwood machine problems. Now, an Atwood machine is named after George Atwood, who was an English mathematician who wanted to study constant acceleration and mechanics. The Atwood machine is essentially a pulley, string, and a system of masses. A free body diagram for this scenario shows that we have the upward force of tension and the downward force of gravity, and this free body diagram is representative for both of the hanging masses as they both are the same mass. So this system is in equilibrium. It is not moving currently. Now, when we do these problems, we will neglect the mass of the string and the pulley. I'll talk to you a bit more about this when we get into the topic of rotational inertia, but we will neglect it. We will also consider any friction on the axle of the pulley to be negligible. Now, let's look at this Atwood machine in which it is unbalanced. We have a mass of 5 kilograms on the left, 10 on the right. The key to solving Atwood machine problems is to identify your system. Remember, you define your system. I've spoke to you about that in previous videos. So let's consider these two masses and the string to be our system in this case. Let's go ahead and do a free body diagram for each respective mass. Now, of course, you'll notice because the mass on the right is 2 times the mass that of the left, I have drawn the free body diagrams to indicate so. Now, one thing that is important that I mention is these are not accelerating currently. These are stationary. In other words, imagine I have my hand on the pulley and I am about to release the pulley in which the system will accelerate. But for these two free body diagrams, I have my hand on the pulley. So we have a greater force of tension on the right when compared to the left. In fact, it's twice the magnitude because force of gravity is twice the magnitude. We have a downward 50 Newton force on the left and 100 Newton force on the right. Okay. So to look at these vectors and the actual objects, you can see I've drawn them on there. And that's going to help us to go ahead and look at what this would be like if the system was released. In other words, I take my finger off and it accelerates. Okay? So first and foremost, you need to understand that when the system accelerates, all objects in here will have the same acceleration. So whatever the magnitude of the acceleration is for the 10 kilogram mass, the 5 kilogram mass will have that exact same magnitude of acceleration. It'll just be going in the opposite direction. So when this system is accelerating, the tension force is constant throughout the string. Students struggle with this. I'm going to show you a calculation here in a minute so you understand. So again, this is after I take my finger off and the system accelerates. This is intuitive because I can look at this scenario here in which the system is accelerating. And by the way, with reference to these free body diagrams, notice the weight, the force of gravity has not changed. But do please notice that the tension force has changed. For the object on the left, the tension force has gotten larger. For the object on the right, it has gotten smaller, but they are equal in magnitude. More on that here in a minute. Let's identify our direction of acceleration as the positive direction. You know by now, you define your coordinate system. And these problems are most intuitive when we define the direction of the acceleration as the positive direction. It's similar to analyzing objects on an incline. If it's moving down in parallel to the incline, let's call down in parallel our positive direction for the coordinate system. Okay? If I take my finger off the pulley, to me it's just common sense that this system will accelerate in this way, in which the 5 kilogram mass goes up, the 10 kilogram mass goes down. Okay, so let's define that direction as positive. Next, you're going to need to sum the forces for your system. If we do this, I use subscript SYS to denote system, and I'm including the tension forces here. Now, I really need you to pause the video and think about this for a minute. So I've labeled each object 1 and 2, so you know what I mean when I say M1, M2 for mass, or T1, T2 for tension force. And so look at tension force 1 here. Well, that is in our positive direction. If you look at tension force 2 here, okay, that is also, or excuse me, if you look at tension force 2 here, my goodness, that is in the opposite direction of our defined positive acceleration. So tension force 1 is going in the direction of the acceleration. Tension force 2 is opposing that, which is why I've subtracted T2 from T1. Then we have M2G. What does that mean? That's this guy here. This is in the positive direction. However, this M1G is in the opposite direction of our defined acceleration. Then the biggest part of all that students just forget, if we're using a system approach, we must sum the masses, no matter how many objects are in our system. So we know the string is massless, it's ideal. We're not talking about it. We're talking about the 2 objects that have mass, the 5 kilogram plus the 10 kilogram, okay? So the absolute value of T1 is equal to T2. That means their magnitude of the tension forces are identical, okay? Which means if we're subtracting T2 from T1, those go away. So they're gone. Tension forces are eliminated from our summation, and I'll show you more on that here in a minute. Now, I want to solve for the acceleration of the system. Why? Because once we find the acceleration of the system, we can analyze the objects separately, because we've already acknowledged that regardless of the acceleration, it must be the same for both objects in magnitude. So what I've done here is I've simply divided the left side of the equation by the sum of the masses to isolate the acceleration of the system. So I want you now to put in these numbers that you have and solve for the acceleration, and you'll find it to be 3.3 meters per second per second. Now, let's go ahead and analyze these 2 objects separately. We're going to calculate the tension force in the string because I want to prove to you that they are the same in magnitude. So let's go ahead and do that, because we know a key piece of information, the acceleration. Force 1 for object 1, the hanging mass on the left. Remember that tension force was this way, and that is our positive direction, and the force of gravity for the 5 kilogram mass is in the opposite. So I'm going to subtract M1G from the tension force. In other words, when using this approach, don't switch your coordinate system up. Remember, we already defined the positive direction, so we need to be consistent with that, okay? And notice here, I'm only including the mass of the 5 kilogram object, and I have this acceleration. We found it using a system approach. So now I can algebraically manipulate this to solve for T1 by adding M1G to both sides. And now I can get my answer that the tension force 1 is equal to 67 newtons. Very cool. Now check this out. We're going to apply the same logic to the second hanging mass. Let's sum the forces for it using the exact same approach, but remember our directions. So M2G was in the positive direction, so I'm subtracting the tension force 2. setting that equal to now the mass of object 2, or 10 kilograms, and our shared system acceleration of 3.3 meters per second per second. So when I manipulate this equation to isolate the tension force 2, I can solve for it to get 67 newtons. In other words, they are the same in magnitude. For the system and our acceleration, it's common sense. Now, we subtracted T2 from T1. So 67 newtons minus 67 newtons is 0, which is why this went away when we solved for the system. Now I've shown you that these are equal. Now, take-home messages on this are very important because I'm about to talk about an elevator again. I'm about to make some comparisons to when we learned about apparent weight and how an object may feel when it's accelerating either vertically up or vertically down. It's the same here for the tension force, and I alluded to that in earlier videos. So if you think back of what these tension forces would be when I had my finger on the pulley, now it's not accelerating. On the left side, it would be 50 newtons. On the right side, again, 100 newtons. But when I let go and it accelerates, the left side goes from 50 newtons to 67 newtons. And the right side went down from 100 newtons to 67 newtons. Let's talk about object 2. It's accelerating downward. Well, how do you feel in an elevator or on acrophobia when you're accelerating downward? You feel lighter. That's your apparent weight. And what you feel when you feel lighter is really that contact force normal upward on your body, which decreases when your acceleration is in the same direction as the acceleration due to gravity. Same here, guys. So cool. So the left side increased because it was going up in the same direction, or in the opposite direction, excuse me, as the acceleration due to gravity. And the 10 kilogram mass is going down in the same direction as little g. And so we see those tension forces change, okay? All right, so we cancel those out, and we're done with our first Atwood machine problem. In the next video, I'm going to teach you about modified Atwood machines. It's going to be great. I'll see you guys in class.